Good morning, everyone. Today for our IQS seminar, we have Jonathan Gross. Jonathan is currently a member of the research team at Google AI Quantum. His work includes characterization and calibration of superconducting quantum circuits, quantum error correction, and quantum metrology. Before joining Google, he was a postdoctoral fellow at the University of Sherbrooke and obtained his PhD in physics from the University of New Mexico under the supervision of Professor Carlton Caves. He also holds a bachelor's degree in computer engineering and piano performance from the University of Arizona. Jonathan, tell us about your wonderful work, please.
All right, thanks, Abhishek. So my talk today is split into two parts because I couldn't decide what I wanted to talk about. So half of it is going to be about the work I'm doing at Google, which is actually fairly close to experimental work. And then the second half will be more whimsical about like quantum error correction stuff that I enjoy kind of keeping up on the side that I got started at when I was in Sherbrooke. So to get started, beautiful. The work that one of the big topics I'm working on at Google right now is trying to characterize the distortion in our microwave lines. The way we do gates, like our gates that change the excitation number of our qubits is by sending microwaves down into our dilution refrigerators. And these microwaves, this is going to work. Yeah, here we go. Need to start at, there we go. Need to start at with our room temperature electronics up at 300 Kelvin, and then pass through multiple cooling stages of the dilution refrigerator through a bunch of different filters until they finally impact our qubit. And because of all of the interfaces in the control chain and all of these filters, the microwave signals that we send at room temperature, that we create at room temperature, end up getting distorted along the way. And it's important to have the microwaves be shaped the way we want them when they hit the qubit in order for us to be able to perform our gates as fast as possible to avoid decoherence and to also avoid exciting unwanted levels of the transmon that creates leakage, which is really problematic for us. Now, there's lots of different ways you can go about trying to characterize these kinds of distortions. I've just highlighted two relevant techniques that people use. One is for trying to particularly measure reflections and compensate for those reflections in the signal chain, which can lead to pulse bleeding from one microwave pulse into another. It causes problems. Another technique that is more analogous to what I'm going to talk about here is to measure the frequency response of our microwave signal chain, to measure a transfer function. And that is to measure how much signals at a particular frequency get attenuated and phase shifted. So if you're not familiar thinking about transfer functions, what I mean by this terminology is the kind of time translation, a linear distortion that my signal can experience. So in the time domain, you could represent this by convolution. In the frequency domain, you represent it by this diagonal kind of transformation, where each frequencies don't get changed by this, but they do get damped and phase shifted. So that means that I can represent my time invariant linear transformation by a function of the frequency, which I call the transfer function. And the way this distorts my signal is I multiply pointwise my transfer function by the Fourier transform of my signal, and then inverse Fourier transform it, and that gives me my distorted signal. We want to measure what this Fourier transform, or what this transfer function is, because if we know it, we can apply the inverse of this distortion to our signal at room temperature so that our qubit sees the shape of the signal that we actually want. Now I'm going to show some plots where I plot down the amplitude and the phase of this transfer function. Ideally, we would like both of these to be flat, where the amplitude is always just left at exactly the same, regardless of what the frequency is, and there are no phase shifts. Now you'll see I'm also representing the frequency as a detuning. This detuning is a detuning from the carrier, because the way we generate microwave signals is by having a high frequency local oscillator that we then mix with some low frequency signals generated by an arbitrary waveform generator. And so when we measure this transfer function, we're usually measuring it in some bandwidth around 0 detuning from the carrier. Of course, you can look at what different kinds of distortion look like in this transfer function picture. So here, if I just have attenuation, broadband attenuation, that would mean the amplitude part would be subunity. If I have a time offset, timing mismatch between when my signal is actually being sent and when I want it to be sent, there's going to be this linear shift in the phase with respect to the frequency. And if I have a reflection in my signal, that will lead to this oscillatory behavior, as at different frequencies, the reflection goes in and out of being constructively and destructively interfering with itself. Great, so this is a slide I'm going to not really spend a whole lot of time on. This is talking about this previous work done at University of Queensland for measuring this transfer function. And involves a lot of different frame transformations in order to keep track of not only what the amplitude of like Rabi oscillations are that are being driven by your signal, but also particularly what the phase of those Rabi oscillations are, because we need both amplitude and phase information. We are going to do a very similar kind of experiment for the Rabi amplitude in order to measure the amplitude part of the transfer function. That's almost identical to what is done in this previous work. But one thing that we are going to do different is measure the phase using parametric oscillations. You might ask why you would want to do something like this. And from a quantum parameter estimation perspective, I can tell you that there's important difference between the Rabi frequency of a Rabi oscillation and the phase of that Rabi oscillation. If I think about this as a Hamiltonian in the equatorial plane of the Bloch sphere generating these oscillations. The Rabi frequency is associated with an eigenvalue of that Hamiltonian, and that's something that I can amplify. So if I drive my qubit for longer, those oscillations build up more and more, and I will get like Heisenberg scaling in my Fisher information. I can more and more precisely measure what that frequency is by just driving the qubit for longer. The phase of these Rabi oscillations is associated with an eigenvector of that Hamiltonian. And that's not something that I can measure more and more precisely just by holding the driving tone longer. And so that really limits how precisely a characterization procedure like this can measure the phase of the transfer function. And you can see this in the data from their paper. Really clean data for the amplitude part of the transfer function. But the phase part of the transfer function is just much harder to measure because that's not something that you can coherently amplify. And we're going to use parametric oscillations as a way of transforming or transferring that information about the phase from an eigenvector into an eigenvalue. But to start off with the simple part, if you just want to know what the amplitude part of your transfer function is at a particular frequency, all you really have to do is drive the qubit with a monochromatic tone. And because we have flux tunable transmons, we can bias our qubit to be resonant with whatever microwave frequency we're sending down. And so you perform some experiments to precisely measure what the qubit's frequency actually is with Ramsey, and then you drive it with a weak microwave tone so you don't worry about AC Stark shifting it too much. And you can measure the frequency of these Rabi oscillations. And that really just tells you what the amplitude of your transfer function is, because you see how strongly the qubit is driven at different frequencies. Now, to characterize the phase, we are also going to drive with microwaves, but it's going to be a more complicated microwave tone. And we're also going to need a phase reference. So anytime you're measuring a phase of something, you almost always have to talk about what are you measuring that phase with respect to. And what we're going to be measuring the phase with respect to is the phase of a parametric modulation of the qubit's frequency itself. So we choose some period, capital T, with which we modulate the qubit's frequency. And we're going to change the phase of this sinusoidal modulation of the qubit's frequency. And we're simultaneously going to drive the qubit with a microwave that instead of being a monochromatic microwave tone, it's going to be a bichromatic microwave tone. So we have some fast oscillations, but we also have a cosine envelope on top of that. And the cosine envelope has the same period as the period of the frequency oscillations that we're driving. And now you see there is a phase of the envelope as well. And we're going to be measuring the phase of this envelope relative to the phase of the frequency modulations. And if you look at your like trigonometric product identities, you see that the phase of this envelope is related to the difference of the phase shifts that the two frequency components in this bichromatic tone experience. So with each of these experiments, what we're going to be measuring is the phase difference between two frequency components. And the splitting of those frequency components is determined by the period. And so by doing a suite of experiments where we change the fast frequency, so like where these two frequency components are centered, and we also change the period with which we're modulating the frequency and also this period of this envelope for the microwave drive, well, that changes the splitting of these two frequency components that we're measuring the phase difference between. And we can collect a whole bunch of like overcomplete information about all these phase relationships and do a massive like least squares fit at the end in order to get a phase part of our transfer function. Yeah, good. I think that's everything I just said. If you run through the math for this kind of thing, you'll work out exactly how the amplitude of the raw parametric oscillations you're driving with this corresponds to the depth of these frequency modulations you're making, and the phase difference between the frequency modulations and the envelope on the microwave channel. But I find that the most intuitive way to understand how these modulations can give you Rabi oscillations that depend on the phase relationship between these two channels is to look at a kind of cartoon picture where instead of doing smooth sinusoidal modulation of the qubit frequency, I think of doing instantaneous pi pulses around Z with the same frequency as the envelope on the microwave line. And you can see what happens if you do a pi pulse around Z in the qubit. For the qubit, what this does is it flips the sign of the microwave. And so before, where I had a microwave where half of the amplitude was positive and half of the amplitude was negative, in this case, if I just drive the qubit with this signal, it's going to like go up a little bit and then go back down a little bit and ultimately not transfer any population to the one state from the zero state. But if I start adding these pi pulses around Z, then I start rectifying this signal and I can make all of the amplitude positive so that I drive Rabi oscillations between 0 and 1. However, this is only going to happen if I have the right phase relationship between these pi pulses and the microwave envelope. If I shift it by a quarter of a period, then I'm flipping the sign of the microwave envelope halfway through one of these positive peaks and one of these negative peaks. And I'm going to make sure that everything destructively interferes with itself. So you go from maximum Rabi frequency of this parametric oscillations to 0 frequency of these parametric oscillations just by changing the phase relationship between what's happening on the qubit's flux line and what's happening on the microwave drive. And we end up taking this data for a bunch of different choices of the phase of the modulation of the qubit frequency, and you get data that looks like this, where you have Rabi oscillations that are sometimes fast and sometimes slow. In the upper left-hand corner is just the fit of all these Rabi frequencies for different phases. And you can see that you can find a minimum, which tells you what the phase relationship is between the two frequency components in the bichromatic tone. And we get really, we're able to get really clean data by doing these experiments because we're able to measure these frequencies with Heisenberg limited precision, because they're Rabi oscillations. We've turned this phase information into an eigenvalue of our Hamiltonian. Now to sort of show you the end result, when we measure this actually on our device and we take that transfer function and apply it to an actual pulse that we might send down to our qubit, you get distorted waveforms that look something like this, where in the dashed line, I have the ideal 10 nanosecond cosine pulse that we might want to send down to our qubit. And in the solid color, I have what we actually measured, where because this is a microwave tone, there's a phase and an amplitude associated with this at each point in time. And one of the main things you notice is that there's little secondary bumps occurring after the main pulse from reflections that we have in our system. As I mentioned at this point, we have all these extra filters and stuff. These have impedance mismatches. Reflections are important. But it's really cool that we're able to measure all this in the frequency domain with enough precision to be able to really resolve these little bumps. And you can even see like secondary reflections. Like this is a main, something like a 5 nanosecond reflection. And then there's a second order reflection from that same thing happening slightly later. If you go back and look at this in the frequency domain, you end up getting transfer functions that look kind of like this. There's all kinds of features to it. We have Gaussian analog filter. You see ripples that are indicative of these reflections that I was showing you in the time domain. There's a slant to the phase part because there is a timing mismatch. Here, the timing mismatch that we're measuring is a mismatch between the timing on our flux control with our microwave control. Because again, whenever we're measuring these phases, we're always measuring with respect to something else. You can look at some of these features a little bit more clearly by removing the timing, the linear part of the phase transfer function from the timing offset and removing the Gaussian filter. And then you see much more clearly just these oscillations from multiple reflections in our system. And then at the end of the day, I told you we wanted to measure this because we would like to remove this by pre-distorting our signal. And so this is one kind of experiment you can do to verify that you're able to actually correct this, which is by implementing the inverse of the transfer function and then just rerunning the experiment. And now we see that we get transfer functions that are flat up to at least like in this data here, I think we see flat up to like 1% variation in the amplitude part. That I want to pause for a second. I might have run through that a little bit more quickly than necessary. So if anyone has questions, this is a good time. In the tradition of my supervisor, Carl, he always liked to put pictures from hikes in the middle of his talk so that if you didn't get anything else out of the talk, you at least got to look at something pretty. This is from recently. I was in Kyoto for a workshop and it was cherry blossom season. So we got some beautiful pictures of cherry blossoms. Yeah. Beautiful.
So on the plots where you're showing the reflection, what's the precision on there?
The precision, how do you mean?
Like on the x-axis before, where you have those colored plots with the phases and everything.
This one?
Yeah, this one.
Oh, like how, like what would be like error bars on the distortion?
Yeah, on the, like, how finely are you sampling the x-axis here?
Oh, the x-axis is sampled once every nanosecond.
Okay.
Yeah.
Okay.
Because that's the sampling rate of the AWGs.
Yeah. Okay.
And you can get a little bit of a sense as to how precise we are on the y-axis by looking at how much noise there is like before the pulse. Because we haven't done anything to like enforce causality in our modeling of this. And so you see little like anti-causal features here. Yeah. And the size of those anti-causal features is like one way of ballpark estimating what kind of precision you have. Yeah.
How much data are we talking here? Because I guess you have to do a sweep across all the frequencies to get all the transfer student phases.
Yeah, it's a lot. I mean, you at the end of the day, almost all the time is spent doing this phase measurement because you have to sweep all these pulses. And so you see we're going out to like about 100 pulses deep. I mean, we constantly keep tweaking these parameters. It takes something like maybe like an hour to collect the data for like one of these transfer functions.
Yeah, to do the whole sweep.
Yeah.
Yeah, because you need to do this for every frequency phase, right?
That's
a lot of data.
A lot of data.
And every actual qubit too.
And you do this for every qubit.
For two.
You can parallelize across the qubits to a certain extent. I mean, you probably don't want to be doing qubits like right next to each other while you're doing this.
No, yeah,
And
but this is
parallelize.
for tune-up as well. It doesn't generalize from one.
It doesn't generalize from one fridge to the other, right? Because you're measuring something about the hardware specific to your fridge. But it is
even cool down to the other.
For calibration.
So calibration, yeah, for tune-up of the bridge. Or
The transfer function changes with the
Yeah,
calibration a little.
that could. I don't know if we've looked at that very closely. The thing we have looked at closely is, so many of our calibrations on like a flux tunable system go stale like incredibly quickly. This measurement of the frequency response of the microwave signal chain is stable over a cool down. Like you can look at it like months later and the transfer function hasn't changed appreciably. Which is, you would like hope for this to be, because you're like measuring something about the cabling, you're like, I hope the cabling isn't changing that much. But there's stuff that you might worry about, like with the phase part of the transfer function, some of these timing offsets are associated with timing of the electronics, and this can fluctuate sometimes because of just like temperature fluctuations at room temperature. So just being able to like have confidence that this thing that you measured, you took a long time measuring to begin with, it's stable over the course of a cool down. So
Yeah, it's going to be my next question is how does it drift in time? But you're saying it's stable for months?
yeah,
Nothing catastrophic changes.
Yeah.
Amazing.
yeah, we were pleased with that.
I mean,
You said that you are only looking for weak driving. How weak are you? So you said that you don't want to look into AC start shift and stuff.
Oh, yeah. So we for most of our experiments, we drive it weekly. We have looked at driving it more strongly just to like investigate, are there like nonlinear effects that are occurring? The nonlinear effects are not strong. I think that just means we're sufficiently far away from like saturating our mixer, which would probably be the source of this nonlinearity. That's not an issue for us.
Cool.
All right. Well, now we can shift gears to something quite different and talk about quantum error correction. And in particular, quantum error correction, where I'm going to privilege the physics of angular momentum. And I'll talk, I'll spend the next half hour talking about exactly what that means and what kind of fun stuff we can do with that. And I want to start by talking about transversal gates. So normally in quantum error correcting codes, we have a code that is built from a physical Hilbert space that's a tensor product of a bunch of qubits. That's like the first thing that most of us talk about. And when we talk about doing gates on that encoded qubit, a transversal gate is usually a gate where we apply product unitaries over those qubits. So in the simplest form, if I want to do a transversal like Hadamard, a logical Hadamard, this would mean that I just apply a Hadamard on each of my physical qubits, and that affects a Hadamard on my logical qubit. And in the Steen 7-qubit code, this is indeed how it works. So if I want to do a logical Hadamard, I can just do Hadamard on all of my physical qubits. Same thing for a logical S gate, which I'm using S for the 90-degree rotation around Z. And then if I want to do a logical C0 between two Steen encoded qubits, I can just do physical C0s between the corresponding qubits in the codes. And then let me back up one second. One of the reasons we like this is because the reason we're building codes out of a tensor product of qubits is because we have some notion that the physics governing our system is local. That means that these local operations are, in some sense, the easy operations we can do, much easier than doing some arbitrary like 5-body unitary. And locality also governs what kind of errors we're trying to correct against. So in the quantum error correcting codes, our notion of distance all has to do with how well can we protect against local errors. So in here likely errors are affected only by single qubits, and these single and 2-body interactions are the easy ones to implement. So they're also easy to implement, and they do not spread errors in a bad way. They don't tend to take correctable errors and turn them into uncorrectable errors. So these are the kind of properties that we're trying to leverage with quantum tensor product quantum error correcting codes when we are asking for like how many things can we do transversally. Now, we have examples of other examples of quantum error correcting codes where we don't have a tensor product structure at hand. And most notably, recently, people have been very excited about bosonic quantum error correcting codes. And so in a bosonic quantum error correcting code, instead of encoding a logical qubit in the large Hilbert space given by a tensor product of many physical qubits, you are encoding a logical qubit in the large Hilbert space given by a harmonic oscillator. And that harmonic oscillator has no tensor product structure on its Hilbert space. It does have structure, though, that determines what kinds of operations are easy to perform and what kinds of errors are most likely to occur in the system. And this is given by like the Weil-Heisenberg representation that you have on this infinite dimensional Hilbert space, displacement operators. The kind of errors you might worry about in a harmonic oscillator are photon loss and dephasing. And the kind of operations that would be easy to do are things like displacements or also Gaussian operations, things like phase shifts and squeezing. And so if you define these like Gaussian operations as kind of like my transversal operations, you can think of the GKP code where you use these grid states in the harmonic oscillator to encode a qubit as allowing you transversal Cliffords, much in the same way that the Steen code allows you to do transversal Cliffords in a tensor product structure. So I've displayed the code words up here for logical 0, logical 1, and then a logical plus and a logical plus I. I'm using Wigner functions because Wigner functions are just beautiful. I also have a strong controversial opinion that in Wigner functions, blue is positive and red is negative. We can debate this afterwards, but I've stood by this for years and I'm not likely to change my opinion. But just looking at these pictures, you can see that how the linear and quadratic Hamiltonians, these Gaussian operations, can do the logical Cliffords that we want. So if I want to do an X operation, flip a 0 to a 1, if you look at the Wigner functions for 0 and 1, you'll see 1 is just a shifted version of 0. So you can do that just by displacing the state. If I want to go from 0 to plus, that is do a Hadamard, you'll notice that the plus state is just a rotated version of the 0 state. And so I can do this by just phase shifting. And if I want to do an S gate, you'll notice that like the plus I state is a sheared version of the plus state. And so I can apply this quadratic Hamiltonian to shear my my phase space and take me from plus to plus I. Yeah, so in many ways, the GKP code is bosonic generalization of a lot of the properties of the Steen code. You have Gaussian operations instead of product operations. The kinds of errors that are correctable by the GKP code do not turn into uncorrectable errors by doing these Gaussian operations. So you don't take like linear errors in creation and annihilation operators and turn them into cubic errors or anything. Gaussian operations are nice because they take linear Hamiltonians to linear Hamiltonians, quadratic Hamiltonians to quadratic Hamiltonians. So we've got this picture of what like transversal might mean in non-tensor product codes. And what I want to spend the rest of the time talking about is looking at different Hilbert spaces that also don't have tensor product structure, but have a different kind of physics associated with them than a harmonic oscillator. And for that, I'm going to look at codes for Hilbert spaces that are governed by the physics of angular momentum, which means that they're Hilbert spaces that carry a representation of SU2. And so an example of this would be like a large atomic nuclei. Those can carry high dimensional irreducible representations of SU2. I mean, you could also look at orbital angular momentum, like the degrees of freedom in a molecule, all these kind of things. give you Hilbert spaces that carry irreducible representation of SU2, and they don't have a tensor product structure on them. In this picture, the easy operations for me to do, the things that are analogous to Gaussian operations in GKP, are going to be these SU2 representatives, what I get by exponentiating Hamiltonians that are linear in angular momentum operators. And the kind of errors that I'm going to think about correcting are going to just be like small SU2 rotations, which means that like these error operators are going to be taken from the Lie algebra of SU2. So they're just in fact my angular momentum operators themselves. And now I want to ask, can I find code spaces within these Hilbert spaces that let me do transversal Cliffords? Like I was able to do transversal Cliffords in tensor product codes, like the Steen code. I was able to do transversal Cliffords in harmonic oscillator with GKP code. Can I do transversal Cliffords here? And what this is going to mean is, can I find a subspace of my SU2 representation where doing the physical rotations, like a physical rotation of my spin by 90 degrees about the z-axis, will affect a logical rotation of my qubit by 90 degrees about the logical z-axis. And similarly, like a rotation of 180 degrees by one of these edges of this octahedron I've drawn will give me a Hadamard rotation on my logical encoded information. Because for the single qubit Cliffords, these are the symmetries of an octahedron inscribed into the block sphere. So I like using this picture. So this means we want to find two-dimensional subspaces of these large spins on which these rotations perform logical Cliffords. If I want to use representation theory, like group theory language, which I'm going to, that means I'm looking for a two-dimensional irreducible representation of this subgroup of SU2. Because these like Clifford rotations are a subgroup of all of the SU2 rotations I could do. Now I told you one example where I might look for these code spaces was like nuclear spin, where we have an irreducible representation of SU2, which means that there is no two-dimensional subspace in there that's preserved by all of the SU2 rotations. But if I restrict myself to just the Clifford rotations, suddenly that large, what was before an irreducible representation, can break up into subspaces that don't mix with the other subspaces. So that's what I'm going to look for here. So when I restrict myself to the Clifford operations, how do these large SU2 irreducible representations break up into things that might work as a code space for me? And this is a kind of technique that some other people like Arlie have been looking at for design codes in other systems when you have just kind of general representations of groups and you're looking at discrete subgroups of these things. So because the representation theory can be very, I mean, it is pretty abstract and maybe not something that all of us are talking about irreps of the Clifford group all the time. I like to walk through what these different irreps are to try and make this a little bit more concrete. And you can do this really nicely with SU2 because we know what all of the irreducible representations of SU2 are. They're just the different spin J systems that we have. And these break up into irreducible representations of the Clifford group in a fun way that you can really quickly see what all of the irreps are. So spin 0 is uninteresting for both of them. Every group has a trivial representation. It's a one-dimensional Hilbert space. Spin 1/2 is also a two-dimensional irrep, both for SU2 and for the Clifford group. This is just our qubit that we know and love. Spin 1 is a three-dimensional irrep, both for SU2 and the Clifford group. And this is, if you can write this in a basis where everything is real. These are just like your real three-dimensional rotations that you're used to for this octahedron. And when you go to spin 3/2, you have a four-dimensional irrep, both for SU2 and for the Clifford group. This I don't have as great of a geometrical picture for. It just is irreducible for both of these things. When you get to spin 2, things start to become interesting because while spin 2 is a five-dimensional irrep of SU2, it is not irreducible for the Clifford group. And so when you break it up into the irreducible subspaces for the Clifford group, you'll find one of them is three-dimensional And it's kind of like the three-dimensional irrep we had in spin 1 over here. But you'll notice that the signs on the matrix elements in the S and the H gates are a little bit different from one another. Do we need to do something with the screen? Pause for a moment.
Other button. Yeah, our screen wigs out occasionally. We just have to power cycle.
Yeah, that'll happen.
There's a much less interesting, beautiful picture as a pause.
Yeah, that's true. Should have brought physical copies of the cherry blossoms.
Remember that new things were going to pop up.
There you go. Awesome. Thank you for that. So anyway, we've got this three-dimensional irreducible representation of the Clifford group, and it's a little bit weird in that like the physical rotation of like quarter turn does a different like rotation on this three-dimensional subspace, but the group structure maps onto itself fine. So it's like interesting. And then you have something happen with the other two dimensions that forms irreducible representation of the Clifford group. And it's not a faithful irreducible representation of the Clifford group. So the Clifford group has a normal subgroup, the Pauli subgroup, because the Cliffords preserve Paulis. And so in this irreducible representation, the Paulis act trivially. So if you do pi rotations about X, Y, or Z, it doesn't change your state, which you can kind of see here when I plot these Wigner functions for these code words on the sphere, because these code words all have symmetry such that if I flip it pi around any of these axes, the Wigner function remains unchanged. The remaining operations that act non-trivially on the code space end up giving you a set of logical operations that are the symmetries of a triangle inscribed in the XZ plane of the block sphere.
Does it pick up a particular plane?
It picks out a particular plane because I chose to label things that way. I think it picks out this plane by my choice of saying this particular basis vector within the two-dimensional code space is 0 and this one is 1. I could make arbitrary choices for that and it would get different triangles. And a cool thing about this code is it's not an error correcting code, but it is an error detecting code for JX, JY, and JZ. So I can detect first order errors in angular momentum with this guy. Yeah, and it's also interesting for a reason because it has this non-faithful action. It has things that are like stabilizers. So I think I'll mention that a little bit later. You go up to spin 5/2, there's another two-dimensional irrep. It's similar to the spin 1/2 irrep, but it's different in the same way that there was those two different three-dimensional ones where the rotations kind of got mapped a little bit differently from the physical to the logical ones. Same kind of thing here. It's a faithful two-dimensional complex irrep, but the rotations get mapped a little bit differently between one another. And then we see our four-dimensional friend from spin 3/2 shows up again in spin 5/2. And that is in fact enough to see all of the different irreps of the Clifford group that we might have. We can keep going to higher and higher spins, but we're just going to see it breaking up into copies of irreps that we've already looked at here. So yeah, this is kind of like the landscape we have to play with. Now these two faithful two-dimensional complex irreps of the Clifford group are candidates for these code spaces I was looking for. So these are two-dimensional code spaces on which I can do logical Cliffords transversally. They only show up in the even dimensional SU2 irrep, so they only show up in half integer spins. And we can find spin 3/2 is the only one where we don't see one of them. However, I haven't yet talked about any of the error correction properties. If you want to check all the nil Laflamme conditions, I mean, there's There's kind of a lot of them if you have three error operators. But the fact that we've built a code space that has this Clifford symmetry means that all these null form conditions boil down to just needing to verify that one of the angular momentum operator expectation value vanishes on one of the code words. And if this happens, then all of the angular momentum expectation values vanish on all of the code words, and everything just works out. So there's a quick check to see if you have a code space that actually corrects your angular momentum errors if you have this symmetry. That's cool. The sad thing is that all of these codes that I have in the red box, or these candidates, don't correct errors. So you might think that it would be like a minor miracle if this expectation value just happened to work out to be 0 when I only had one code space available to me. However, we're saved when we go to higher spins because you can see that these irreducible representations of the Clifford group start showing up with multiplicity, which means that I kind of have a choice as to what I choose for my logical zero. There's a two-dimensional subspace of candidate logical zeros. And in all of the cases that we've looked at, whenever you have this choice, one of the choices has a positive expectation value for JZ. One of them has a negative expectation value for JZ. And you can engineer this superposition among this like basis you chose for this logical zero space, such that you get a logical zero under which the JZ expectation value vanishes. And then you have an error correcting code. So that's cool. You can do this from spin 17 halves and above, and also in spin 13 halves. These are kind of large, like we don't have a lot of like nuclei running around with spin 13 halves. There's of course other systems that have spin 13 halves running around, but it'd be nice to find an example in a smaller spin. So to do that, we're going to look at a different set of logical unitaries. So the Clifford group, one of the reasons the Clifford group for a single qubit is interesting is that the Clifford group is a maximal subgroup of SU2. So that is, there's no larger subgroup of SU2 that contains the Clifford group that is not all of SU2 itself. There are other interesting, there is another interesting maximal subgroup of SU2, and that is the icosahedral group. This is the set of rotations on the Bloch sphere that would preserve an icosahedron that's inscribed in that Bloch sphere. We don't use this as much, but it's a valid set of gates that you might think about doing transversally. And if you go through this whole exercise I did with the Clifford group looking for these two-dimensional irreps, you'll find that there exists a two-dimensional faithful irrep of the icosahedral group in spin 7 halves. And in spin 7 halves, that miracle I was talking about does in fact occur. And this code space happens to be error correcting. And it's pleasing in another way too, in that because I've got this irreducible representation of SU2, you might think that the JX, JY, and JZ errors need to map to orthogonal subspaces if I'm going to be able to correct for all these things. So I need to have a two-dimensional code space, and I need my 3 independent errors to map to 3 orthogonal two-dimensional error spaces, which means I need to have at least 8 dimensions available in my Hilbert space. And spin 7 halves has exactly 8 dimensions. So it's kind of this very efficient, like perfect error correcting code with the icosahedral symmetry. Okay, great. Now I just want to finish up with some extra topics that thinking about these kind of codes has led us to explore. One question you might ask about these is, I've been talking about like irreducible representations of SU2, like nuclear spins. These representations of SU2 can also show up in tensor product structures. Like oftentimes when we're taught about angular momentum, you start thinking about these irreducible representations of SU2 as being the totally symmetric subspace of a collection of n spin 1/2 particles. So I could encode my information in the totally symmetric subspace of n spin 1/2 particles. And you might ask, is my code going to correct against local errors on these qubits? Because I didn't design it to correct against local errors in any tensor product structure. However, what you can show is that because you're working in the totally symmetric subspace and you've designed a code that corrects the angular momentum errors there, that also means that you're going to be able to correct local errors if you actually instantiate this in a tensor product of spin 1/2 systems. So that's pretty cool. You can look at higher orders of the angular momentum operators, making sure that their expectation vanishes gives you larger distances in your code. So JZ vanishing gives you distance 3, JZ cubed vanishing gives you distance 5. You can continue to like bootstrap your way up to larger and larger distances if you wanted. However, like this has all been great stuff so far. These codes, however, have not been built to be like nice to do the syndrome extraction on. Like the Steam code, I talked about how it has these weight force stabilizers, and you can measure these things. There's nothing like stabilizers for these spin codes the way I've described them right now. Particularly like the icosahedral code. It's not additive. There are no stabilizers you can define for this if you instantiate it on 7 qubits. Performing entangling gates is also hard. For GKP, you can do the 2 qubit Cliffords also with quadratic Hamiltonians, so Gaussian operations. That's good. Gaussian operations don't turn your correctable errors into uncorrectable errors. For the spin codes, you might think in order to create an interaction between 2 of these spins, you're going to need at least a quadratic Hamiltonian. So something like JZ. And the problem with SU2 is that these quadratic Hamiltonians don't form a closed algebra. When you start doing commutators of the quadratic Hamiltonians with other things, you start getting higher and higher order of Hamiltonian terms. So there's an extra challenge in trying to figure out how to like interact these codes with the SU2 structure. And this is why I made that point earlier. Well, going back to the question of how to like measure the syndromes. For the Steen code, were able to define stabilizers, which were like local operations that acted trivially on the code space. And this means that we actually might be interested in this non-faithful representation of the Clifford group that I showed up in spin 2. Because since the Paulis act trivially on the code space, the physical Paulis act trivially on the code space. Those act like stabilizers, and you can measure those operations and project yourself into like the joint +1 eigenspace of the Pauli X, the physical Pauli X, physical Pauli Y, physical Pauli Z, and that projects you into the code space. That's cool. That's analogous to stabilizers that we're used to thinking about in tensor product codes where the stabilizers are Pauli strings. One thing that is different is that in the stabilizer codes with qubits and Pauli strings, the different syndromes kind of foliate the full Hilbert space into like kind of identical subspaces. So like totally +1 eigenspace is one code space. If you change one of those eigenvalues to -1, you get a different 2-dimensional code space. All the different permutations of plus and -1 give you different like 2-dimensional code spaces. And in some of these codes, you can just like keep on computing in those different code spaces. They all work just as well. Here, the different eigenspaces of these physical Pauli X, Y, and Z have different dimensions. So the totally +1 eigenspace has dimension 2, but the other ones don't necessarily have dimension 2. So you can't just kind of do Pauli frame tracking like you might be used to doing with a service code, which is another complication for how you would actually use these in practice. On a somewhat tangential line, these error correcting code spaces have also found use for metrological purposes. People use one-dimensional like GKP code spaces, these so-called like sensing states, as tools for measuring X and P position and momentum displacements simultaneously, modulo pi or something. Because these grid states allow you to really allow you to see both of those displacements as commuting. And so we can do something similar if we want to try and sense SU2 parameters. And of course, the generators for SU2 don't commute with one another either, but we can find optimal sensing states by building one-dimensional code spaces that have symmetry. In particular, what you need is tetrahedral symmetry, which is a subgroup both of the icosahedral symmetry and the octahedral symmetry. If you build one-dimensional spaces that have this symmetry, those end up being excellent for measuring displacements in SU2. You can also have fun and stop limiting yourself just to SU2. You can look at what happens if you go to SU3 or more general SUD. We've played around a little bit with this. I don't understand, I've begun to understand more the representation theory of SUD, but I don't understand it as well as SU2. So we've just made some beginning forays into finding code spaces that do this. But you can look for things that have like symmetry of the discrete Heisenberg group, which is like the analog of the Pauli group in qubits. And then finally, there's this kind of interesting question that I've had in the back of my mind for a while, which is when you think about the GKP code from this perspective of a representation of the Clifford group, what you really have in GKP is a code space that is an irreducible representation of this thing like PSL2Z. So this is this discrete set of Gaussian unitaries. So there's a discrete set of shears and rotations that preserve the code space. And this is it's an infinite group. It has a bunch of normal subgroups. There's a set of these shears and rotations that act trivially on the code space. So that's a normal subgroup. And if you quotient out PSL2Z by that group that acts trivially on the code space, you get the Clifford group. That's this triangle group. PSL2Z has a lot of other interesting normal subgroups that you might think about quotienting out by. One of them, when you quotient out by this discrete subgroup, you get the icosahedral group, which is kind of suggested that maybe in the oscillator also there exists a two-dimensional GKP-like code space on which you could do icosahedral unitaries transversally. So I think this is an interesting open question to pursue, see if that actually turns out to be the case. And I think with that, I have one last picture that you can look at if the icosahedron was a little too much, and I'm happy to take more questions.
It occurred to me while you were describing this, because I haven't heard about any of this stuff before, that there's a connection to resource theories in some sense, right? So you can imagine taking a set of sort of non-resource creating operations as your set of errors for an error correcting code. And there you don't necessarily have the structure of a group. It would be something more general, like a category or something like that. So have you thought about generalizing error correction to that kind of?
I have not. But you're saying maybe in this like angular momentum setting, there's a resource theory.
In the angular momentum setting, it would be the resource theory would be the resource theory of asymmetry with respect to that group. And then, but what you're talking about is you take the easy operations according to resource theory and you say, well, these are the errors for my error correcting code. There seems to be sort of some kind of mapping between the two.
Oh yeah, there's like a map, they're almost like the same.
Yeah, I mean, it's like, well, except in the error correcting case, you're looking for states that are not disrupted by these operations, whereas, or subspaces, whereas in the resource theory case, you're looking for the opposite. But there seems to be some kind of close mapping between the. So you could look at things like, I don't know, the thermal resource theory, for instance, and say, well, suppose that there's operations called thermal operations, which can't generate non-thermal states basically.
Right.
You could say, well, what if I had an error correcting code where those were my errors, which would be something like saying that your errors are thermalization.
Mhm.
And that's not a group, but it's
Mhm.
has a similar structure. Like there's a category theory structure that generalizes that. I wonder if you could make an error correcting code for that from this kind of idea.
Yeah, that would be nice because oftentimes, like you're saying, that the errors don't have this group structure. Sometimes you're kind of saved. Like I said,
Can't use the representation theory.
yeah, because here I said that my errors I wanted to correct were like small SU2 displacements. That is a group, but because of like the linearity of the error correction conditions, I can also correct like complex linear combinations of these generators. So I can correct things like relaxation, J minus errors. So sometimes just by like complexifying the Lie algebra, you get errors that don't form a group, but that you do care about correcting. But you don't always, that doesn't always give you all of the set of errors that you want to correct. So I could see that being interesting. If the like resource theory perspective would give you a tool for building that, like evaluating when you have that.
Because some of these things have been worked out, like not in general, but for some specific cases that are not group structure.
Yeah.
Code's theory of coherence, theory of thermalization, on this kind of things. Be worth looking at.
That'd be cool.
Questions?
So going back to the first part of your presentation.
Yeah.
The sensing of the phase error. I was wondering if you guys have looked at all into taking the Fourier transform of the state vector itself and going into the Fouquet picture and trying to do measurements on the quasi-energy. Because that quasi-energy, as long as the do you know what I'm referring to here?
Yes, I mean, this is kind of what we're doing when we're doing the parametric oscillation.
Yes.
If you have a Fouquet Hamiltonian.
Yes.
Just looking at periods. So I think we are measuring quasi-energy.
Your eigenvalues are the quasi-energies.
Yes.
They should be, yeah. And as long as that signal is exactly on resonance with the qubit, that quasi-energy should be the Rabi frequency.
Yeah.
But so something that we've been working on is we found that this quasi-energy actually has a sensitivity to the phase offset. And it's mixed in with everything because if your phase oscillates, the frequency profile of your signal, if only momentarily, is going to drift away from
Yeah, here you're talking about the phase of what?
phase of the signal,
Of the microwave.
microwave.
So if the microwave phase is not, like, I'm assuming it's constant here.
Yeah, and if
You're
it
saying if
drifts,
it's fluctuating.
if it drifts at all, then the frequency profile of that microwave is going to shift. It's no longer a Rabi drive. We found that the sensitivity of the quasi-energy to that actually has a linear factor that is missing with that sensitivity to drifts in the amplitude. That is the amplitude of the drive. So by shifting, by modulating that amplitude and sampling at different amplitude strengths, I imagine that you could be able to separate out what is sensitivity to phase error versus sensitivity to amplitude error, for example, and that potentially could be done with less measurements than this.
So you're suggesting that maybe there would be a smaller scan of amplitudes that you could do, and by looking at.
Just by sort of modulating like what sort of noise the qubit is going to be sensitive to, you can operate it in one regime where it's mostly sensitive to amplitude noise, for example. And then you can operate in a different regime where it's mostly sensitive to phase noise. And that I'm imagining it probably won't be as accurate as this other method that you're doing now, but potentially done with less.
That's an interesting idea. Maybe we could chat about it more.
Yeah, I'd love to chat more about that.
Have you looked at anything apart from cosine pulses? Or the envelopes on your?
On the microwave gates, actually. Yeah, I mean, one of the reasons for characterizing the distortion precisely is to like open up yourself, be able to do fancier pulses.
Not a question, but a comment. That one Wigner plot in the second part that had a light background, that wasn't from your stuff, was it? Because the blue was negative.
Oh,
That one.
this one is not mine.
The one on the left?
The one on the left, oh God, yeah, I didn't make the plot, but a collaborator
There you
did.
Of all of the things to notice.
Yeah. Well done, well done. It's gonna flip off of that again.
Uncomfortable.
We'll
Also,
cut that down.
what hike is that picture from in the middle of your? presentation?
Oh,
Where is
Yeah.
that?
It's in Kyoto, or actually, it's a little bit east of Kyoto.
Imagine
There's
some
a-
of the cherry blossoms.
Yeah, they do this like light up at night.
Yeah, it's
The
beautiful.
cherry blossoms. So this was at a Buddhist temple, east of Kyoto. We were directed to, and it's not beautiful. It's very pretty. Beautiful.
Probably a good note to end on here and we can take discussion.
Let's thank Jonathan once again.